Thorium: Extraction and Applications. Discovered in 1828, thorium is a naturally occurring radioactive metal with the symbol Th and atomic number 90. It's part of the actinide family, the same group as uranium. When freshly cut, thorium is silvery white, but it quickly forms a thin gray oxide coating after exposure to oxygen. It is found mainly in minerals such as monazite and thorite, usually mixed in with other rare earth elements. Monazite sands are a key source of thorium, as they contain minor but significant quantities of thorium oxide. These deposits are found in India, Brazil, Australia, and parts of the United States. Since thorium is usually mixed in with other rare earth elements, it's often collected as a byproduct rather than the primary goal. The extraction of thorium typically begins with monazite sands, which are phosphate-rich mineral deposits found in beach and river sands. It is also found in veins that contain thorite and other rare earth minerals. These sands are mined and then processed through physical separation methods such as gravity, electrostatic, and magnetic separation to isolate the denser monazite grains. Once the monazite concentrate is obtained, it undergoes chemical treatment at facilities that can safely handle low-level radioactive materials. The most common method of this chemical treatment is alkaline digestion using sodium hydroxide at high temperature, which breaks down the phosphate matrix and allows thorium hydroxide to be separated. From this step, the thorium is recovered as thorium hydroxide. An alternate route involves acid digestion, where sulfuric and hydrochloric acid is used to dissolve the mineral, creating thorium sulfate. Further purification, either through solvent extraction or ion exchange techniques, is then required to remove uranium and other rare earth elements, since these are commonly associated with thorium-bearing minerals. The final product of these two processes is thorium oxide, which is stable, has a very high melting point, and is suitable for applications in ceramics, alloys, and as nuclear fuel. It's important to emphasize that each stage of extraction and refinement requires strict handling procedures due to both the radioactivity of thorium and the presence of uranium byproducts. This is why most modern research focuses on refining methods that minimize environmental impact and improve worker safety. Reaching high purity is crucial, especially for nuclear fuel work where even the small impurities can cause large problems. For some uses, the oxide can be converted to halide salts, which act as a stepping stone for producing metallic thorium through high temperature or electrolytic processes. Because of the radiation precautions and extreme heat involved, these steps take place in shielded or remote operated facilities. The finished metal is quite ductile and naturally resists corrosion thanks to a thin oxide film on its surface. As previously stated, thorium has recently drawn significant interest as a potential alternative resource for nuclear energy. The most abundant isotope, thorium-232, is not directly fissile, meaning it cannot by itself maintain a chain reaction. However, once inside a reactor, thorium-232 can absorb free neutrons and, through a sequence of nuclear changes, transform into uranium-233, which is capable of sustaining fission reactions and releasing large amounts of energy. In this way, thorium functions as a fertile material, a precursor that can be converted into usable nuclear fuel. Advanced reactor designs, including molten salt reactors and heavy water systems, are being investigated to make practical use of this pathway. Such approaches hold the promise of extending the fuel supply, reducing the production of long-lived radioactive waste, and enhancing safety compared with conventional uranium-based systems. While the use of thorium oxide outside of energy production has been limited, Its high melting point and chemical stability have proven useful for lab crucibles and high temperature ceramics. It has also been used to improve the clarity of optical glass and as an ingredient in tungsten electrodes for certain welding processes. Even though thorium gives off less radiation than many other actinides, it is still an alpha emitter and needs careful handling. The biggest risk is if thorium dust or its decay products are inhaled or swallowed, since alpha particles can damage tissue at close range. Modern labs use glove boxes for powders, good ventilation, and safe storage of residues. Mining and refining operations must also keep an eye on radioactive tailings, making sure that they're contained and don't leak into water or soil. Interest in thorium based energy keeps growing. India's Advanced Heavy Water Reactor program is looking to use its large mineral reserves, while projects in China and Europe are re-evaluating molten salt reactor designs. Current research focuses on making fuel, testing how it holds up under irradiation, and closing the fuel cycle to reduce waste and improve sustainability. Even though there are still technical and cost hurdles ahead, thorium remains a strong candidate for a long term, low carbon energy strategy. In summary, thorium is an abundant element mainly found in phosphate and silicate minerals. With mining, separation, and refining under strict safety controls, it can be produced as both an oxide or a solid metal for special uses. Its mix of stability, high temperature strength, and nuclear potential has led to applications ranging from laboratory crucibles and high performance ceramics to even medical imaging agents, a practice now discontinued because of our greater understanding of radiation risks. Ongoing research highlights thorium's potential to support cleaner, more sustainable energy systems.